Yeah, so first of all, the good old days of data mining long ago, yeah, so data generation in that time, so 10 years ago, maybe 15 years ago, data generation and to some extent also data storage was costly. Yeah, I know it's hard to imagine because nowadays everybody, thanks to our smartphones and stuff like that, is producing data just virtually at no cost. Yeah, of course they cost something, battery power or money for the provider or whatever. But somehow data generation and data storage nowadays is really cheap. And 10 to 15 years back, that was actually not the case. So in those days, domain experts typically very carefully considered which kind of variables, features, whatever to measure, to generate actually. Yeah? So data typically was derived from some specific experiments. So domain experts were extremely careful when they designed the experiments. What kind of data should be really recorded and what actually not. Yeah. So the consequence was that the data back then, the data sets were very well designed and potentially contained only the relevant features and typically also only a small number of features. And typically those features were extremely relevant. Yeah? So in the days back, we wouldn't have things like this where we just generated data and for some reasons there are multiple semantic concepts in. Yeah? But at those days, people were really considering what are the really important features for my application, for my semantic concept that I want to explore, and that's what they actually recorded and nothing else, because it was simply too costly to just record anything, so to say. Yeah. Of course, that somehow changed. I just indicated it, but also we, as a kind of data scientists, are somehow responsible for that, because we told people when they had the opportunity to just produce more at lower costs, we told them just produce as many things as you can. We can do that. We can handle that. Yeah, we as the data scientists, we can do that. We can handle that. Actually, okay. It's a little bit different, but anyway, let's have a look at the slides here. So generating and storing data now, it's easy and cheap. People tend to measure everything that they can and even more, okay, including even more complex feature transformations. Yeah, no worries. And what I just said, we said no problem, just do it. We can analyze that data. We can do that from multiple sources, and so just record anything you can. We can stand it. Okay. But the consequence now, of course, is that we typically have data sets with many features, containing a large number of features. Yeah, but the relevancy of each feature for the analysis task or for the goal of the analysis is not really clear, because actually nobody just cared when recording the data. We just record the data and not think about it. So it's like first shooting and then asking the question. Back 10 or 15 years earlier, people first of all asked and then shot, maybe. Yeah, but nowadays we just shoot and then ask later on. Yeah? And that is of course somehow a problem, because we got a lot of features and we don't know, we are not clear about, do we really got the most important features, the relevant features, and are really all features really relevant to what I'm actually supposed to do? And the answer to this question is, in most of the cases, no. There are a lot of irrelevant features. We can be very sure if we have, 50 or 100 features or even much more, most of them are, or a lot of them are just not relevant to our task. Okay, is that a big deal? Well, we will see. First of all, just that you know, high dimensional data is not a myth, is really happening. So image data, of course, if you don't do the representation learning stuff, the deep learning stuff, you can still work with low-level image descriptors like color histograms, texture, shape information and stuff like that, or with regional descriptors. Then you end up typically in some kind of thousands of features for an image, yeah, for just an image. So an image is transferred into some kind of 1000-dimensional feature vector. Data from medicine or biology. So, for example, metabolome data. We worked with metabolome data 10 years ago, actually. So that was the first part of high-dimensional data for us. Yeah? So the features represent concentrations of specific metabolites, so that are intermediates in the results of the metabolism in the body of people. And we actually had a data set of the so-called Bavarian newborn screening. So this is a program in Bavaria. I don't know if they have the same here in Schleswig-Holstein, probably. So they take from each baby, they take the blood concentration or blood, and then measure the concentrations of, in that case, 43 metabolites in the first 48 hours after the birth. Yeah, and from that they want to somehow define or derive if the baby has some specific metabolic diseases, or at least has the potential for metabolic diseases. Yeah, and this data set had actually between 50 to up to 2,000 features, and we had to somehow analyze that 10 years ago, and that was actually for us as a research group one of the first stages where we actually touched or got in touch with high-dimensional data. So even 50 dimensions can be quite high, because you don't know if all the 50 metabolites are really, really important, or the concentrations of the metabolites, of course, are extremely important or are important at all for some metabolic diseases. Of course, the doctors somehow thought about it, but they said to us, it's just a guess. Yeah? It can be that we miss some important metabolites, but we hope that we got all. Yeah? But we don't know if some of the metabolites we actually measure are really important for some diseases or not. Yeah? So a typical question of the relevancy of features. Yeah. Also, some example from my early days as a PhD student. I worked a little bit with microarray data, which is some data that is now deprecated, I think, in the bioinformatics domain. So the features corresponds to genes, actually. Yeah. So we take or people at that days took again blood concentrations or whatever, actually, so some samples from different patients, and they measured how the different genes have been expressed in the cells of these patients. Yeah? And well, if you think about how many genes we have, we may have a lot of features. Yeah? For each gene, one feature. So in that case, they typically measured 20,000 genes for one patient. So each patient was a 20-dimensional feature space, yeah, of each representing one of the genes. Yeah? And in that case, even because we didn't have the data for 20,000 patients, we just had 1,000 patients, a set of 1,000 patients, but the dimensionality was much larger than the number of samples we had, the number of data objects that we have. Yeah? So the data matrix was a little bit squeezed. Yeah? Yeah, and also a very prominent example probably is text data, which you probably know. We can model text data with term frequency values. So features correspond to the frequency of words, and depending, of course, on the dictionary we use, we can have a small dictionary of a couple of thousand words, but very often we have hundreds, even hundreds of thousands of words. Yeah, 50, 80,000 words typically. Yeah, so we have 80,000 dimensional feature vectors. So a document is 80,000 dimensional feature vector, and that is often, very often used for text analysis. Nowadays, again, we use a lot of deep learning approaches also in text data, but still we are working with text frequency, term frequency, TF-IDF, term frequency, inverse document frequency features. Yeah? So high-dimensional data is not a myth; it's actually there. Yeah? Especially if we have very, very complex data and have to transform that into some canonical representation, like feature vectors. Yeah. So, what are the problems actually? Why should we care? Well, we have a lot of maybe irrelevant or even misleading features that represent different semantical concepts which we are not interested in. So what are actually the technical problems here? Yeah, and we just given an overview of what's coming up. So to say, we'll talk about all these different things on some slides here in more details, but here's just an overview. First of all, the distance will grow. Yeah, if we have higher dimensional data sets, we take the sum of the feature-wise dissimilarity, for example, in the Euclidean distance. So the sum will be higher, so the distances will grow, and that will lead to a loss in contrast of distances, which is also called the concentration problem. Also, the meaning of the neighborhood concept will be not existent anymore. Yeah? We will have a growing data space, which is kind of related to the distance, the problem of growing distances, meaning that we also have a growing hypothesis space. Yeah? We will have, with the growing data space, also a kind of empty space problem, and we'll see that the tails of distributions will be much more important than other things. Yeah? So Gaussian distributions behave completely unexpected and unintuitive, as we will see, and will have the problem of these different semantics layers, and so on and so on. So there are a lot of much more problems that could be summarized by the term of cursive dimensionality. So we will only focus on these things that are somehow related to what may actually happen to our patterns or to our data in these high dimensional spaces. Yeah? We're not talking about computational things like, hypothesis spaces growing is a little bit about efficiency also, yeah? But of course, high dimensional cases, high dimensional spaces also very often mean that we have to spend much more computational effort to find something, to compute something or whatever. Yeah. So now let's have a look at all those different things a little bit closer in the remainder here.